Welcome back. This is Ted Bendixson here, and today we're continuing along with our journey of making a game from scratch on the Mac. You may see or hear a little bit of a difference. I actually got one of these microphones, so it's noticeable to me. So hopefully we'll have better audio quality. My voice will sound a little bit more clear. That's kind of the goal. So if we're looking at where we are, where we last left off just a few days ago, we've got basically we've got a screen that will more or less draw the clear color. So if we go into this and we run it, right, we've got like a green screen, and that green actually matters because that green is the same clear color from metal. So if we actually look, so we actually are drawing into a metal view that then gives us like a green kind of a color. So if we look here, have a bunch of stuff, a bunch of notes. We did a bunch of, working with dispatching semaphores and having triple buffering for a frame. So that is actually going to set us up to do this next part. So now that we can kind of at least get metal to do something for us, we can have it make a clear color, or we can have it draw geometry. And so some of the geometry that we're going to have it draw, we're going to have it draw just some regular boring old triangles in like a two-dimensional space. That's going to at least be the start of it. And then we're going to kind of move forward from there. So what I'm going to show you is pretty close to what you would get just by default with metal. And then what we're going to do is we're actually going to kind of tweak it so that we can draw two-dimensional games. Because the idea is with metal and with many of these kinds of, with many sort of rendering or languages, the default behavior is three-dimensional drawing. And if you're just doing 2D games, or if you were just doing like a two-dimensional application, kind of like what we are doing, which is pretty much for the purposes of prototyping something, it's for the purposes of prototyping gameplay. What I found is that it's actually possible to prototype quite a lot of gameplay to get a sense of how something, to get a sense of what something is going to be like, mostly in 2D, which is why I like to start a lot of game projects just in 2D and then kind of like work my way up from there. I think if something works really well in 2D, there's a much greater chance that it's going to work really well in 3D. And so that's why we're starting with 2D. So the idea is to get from Metal's default way of drawing things in 2D or in 3D to kind of like forcing it to draw things in 2D, and then kind of once we have a great game that plays well in 2D, we can consider moving it over to 3D. That's at least my thinking, and I feel like there's a lot of precedent for this kind of thing, especially in the game design community. Sort of the canonical example that I like to present is Slipways, right? So Slipways started out just as this 2D game with sprite art, but then once he found that he really had something worth expanding on, and that there was like actually a community for it, then he kind of went really hard into making that game 3D and doing all those things. So that's a similar kind of process that we're going to be doing here. So the very, very first thing that we're going to do, actually, we're going to learn how to draw just solid blocks of color in metal, solid blocks of color with just triangle geometry in metal. And so to do that, we need to start talking about how to get this render encoder, this MTL render command encoder, to draw some geometry. And if we're looking at that a little bit more closely, the first thing I would do is I would look at, okay, MTL render command encoder. So, again, we're just gonna look up the documentation here. Actually, I'm gonna make my size a little bit bigger so you guys can take a look at that. So, command encoder. So somewhere in this MTL render command encoder, we're going to have an option to, okay, so there's a few different things. You can already see that this is going to actually it's going to be useful for it's pretty much going to be the one thing that we use to do render commands. So render pipeline states, MTL render pipeline state is actually a very, very important idea in Metal. It's pretty much the same thing as a that's how you set your shaders, your fragment shader and your vertex shader in Metal. And so we're gonna actually create those in a separate library. We're gonna use the Metal compiler to make one of these MTL render pipeline states just for drawing like a solid block of color. So we're gonna have it compile that Metal code. And then we're gonna actually have the application load that Metal code from that library at startup. And it's going to load the vertex shader and the fragment shader at startup. And then what it's going to do is we're going to turn that into what's called an MTL render pipeline state. And we're going to use that thing to actually tell the system how to organize the triangle vertices and how to basically what to draw and how to fill in the triangles. So that's how to look at that. I'll kind of just give you a quick overview. Basically, everything in modern graphics is done as some variation of filling in a triangle. There's some very important mathematical reasons for that. Triangles have this special property where at any one point in time, like three vertices on a triangle, 3 points actually define a plane. So there's always a plane that's defined by 3 points. If you think about it, if you actually had like a 4th point, like let's say, why isn't it a square or why isn't it just 2 vertices? Well, 2 vertices isn't really enough to give you a plane. So if it was only 2 vertices, you would just have like a line segment. You could have a line segment in 3-dimensional space, but that's not enough to define really a plane in that space. It's not enough to define something that you could fill in with a texture or a color. If you have like a quadrilateral, right? So 4 vertices, that isn't always a plane because it's possible that one of the vertices you could have like a triangle for like part of it, and like let's say I have like a triangle here for like part of it, and then the vertex here, like it could be kind of bent like this, and then I would have 2 triangles and I wouldn't have a plane. So basically what it comes down to is 3 vertices is enough in mathematics to define a plane. And that's how pretty much all 3-dimensional drawing is done on modern computer hardware. It's basically the conceptual model for most of how drawing is done. Now that's going to be changing actually soon because of what you can do with ray tracing. Pretty much that just changes the entire model of how a game scene is drawn from drawing polygons, triangles all over the place, to actually simulating light reflecting off of surfaces. So that's kind of coming in the future with more modern graphics hardware. But for the purposes of like making a 2D game and just prototyping a gameplay idea and seeing how something feels when you're playing around with it, we're just going to stick with, the standard drawing triangles. So basically everything that we're talking about is some way of drawing a triangle and getting set up to draw triangles, because if you think about it, triangles are a triangle defines a plane in 3D space. So with that kind of out of the way, let's get to talking about some of this metal code and to talking about a render pipeline state. So if we look at this, like let's look at some of the documentation here for MTL render pipeline state, an object that contains graphic functions and configurations state to use in a render command, right? So what we saw was that we can set the render pipeline state on an MTL render command encoder, which is going to tell the system how to draw a frame. And this render pipeline state, it's graphic functions and configurations. So we want to set up one of these things so that we can, create one of the, we can actually load one of these in. So this actually has a few different functions that we can use to set up a render pipeline state. And if you're just looking through the documentation, it's not entirely obvious, but we can look at this one, new render pipeline state with descriptor. So something needs to make one of these, right? New render pipeline state with descriptor. Okay, and that is a function of MTL device. So already we can kind of hop into our code. We can sort of set up the kind of the boilerplate here of what we're going to be doing, and then we're just going to kind of gradually fill that in. So let's take a look at some of that. And since this is actually happening in the main function of the game, so this is when we actually start up the game. This is kind of what we're going to be doing. So let's look at so metal device, right? Let's see. Yeah, I think we'll do it after we, right after we render pipeline descriptors. Okay. So if we just look at the documentation, we're gonna just copy. We're just gonna yank this straight out of the documentation, right? And I'm just gonna copy that. Okay. Okay. So the thing that we're getting, I'm just gonna call it. Oops. Gotta love Vim. Solid color pipeline state. That's just to kind of give me a sense of what it is that we're actually going to be drawing here. And we're going to use the metal device to create one of these things. And then if you're using Vim, you can use capital J to bring a thing up. That combines previous line. So new pipeline state with descriptor. This is still, we need to make a MTL render pipeline descriptor in order to fill that in. And then a possible error. So I think, the error thing, we can just, set that up. A lot of times what I like to do with games or applications that I make, I'm kind of a stickler for things being, if you didn't get the initial setup totally perfect and totally right, or if, let's say that there was an error or something like that, I like to just have the app hard crash right away, instead of trying kind of trundle along with stuff that is totally a dependency that it's like, if we can't tell this thing how to draw some triangles, then this thing just shouldn't run. So a lot of the error handling that we're going to actually do in the initial application here, it's just going to be, look, if there was an error, hard quit, and tell people why you hard quit so that the programmer can fix it. So that's my preference. So we can just do nil, and we go. So we'll pass this error in here. That's Apple's error class, and then so that's that. And then again, I'm just kind of following this backwards. So we definitely need to make a render pipeline state we need to now the next thing that Apple's asking us for is to create an MTL render pipeline descriptor. Well, what's one of those? How do we make one? Let's find out. So we can click on this. What's kind of nice is you can just sort of like work your way through the documentation to find things. An argument of options you pass to a device to get a render pipeline state object. Okay, great. How do we create one of these things? MTL render pipeline descriptor, okay. This probably has some kind of a initialization function, right? So let's look at that. Da, 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 da. And this is, like I said, this is sort of the object-oriented boilerplate that we have to do. Function. So reading this, then configure and use the descriptor using a, okay. It may actually be the case that we can just do a standard alloc and init. So this thing, I'm just reading the, okay, so this is a class. Okay, it comes from NSObject. That's, if you read like the inheritance kind of stuff here, if you see that something inherits from NSObject, that says a lot about whether or not the initializer for the class is going to be really simple, or it's going to be like, oh, I got to pass all these parameters into it. This looks like it's fairly simple. My guess, just offhand, is we can make one of these things just using alloc and init, and then we just set all the properties. So that's kind of my guess. So let's try that and then see if that works. You know, a lot of this is how I do a lot of software development, is I just do kind of like little pieces at a time just to figure out. Oh, come on, Apple. You know that my I really should just have that thing at the bottom. I shouldn't have the okay. So let's just say so this is MTL render pipeline descriptor star, solid color. Let's call it solid color pipeline descriptor. I don't know, desk. I like long names. I'm a big fan of those, just because, you know, it's more descriptive. I'd rather like read a long name and know what I'm talking about than not have one of those things. Then kind of be confused about what something is. Okay, so we're going to do just alloc and init, and what that is in Objective-C, as I said, this allocates memory, so this is a memory allocation, and then this just like sets it to 0, basically. It does all this stuff kind of under the hood because it is an object-oriented language, so it's hiding some of the data that's there. So now, the really important thing that we need for this pipeline descriptor are the vertex and fragment functions. Actually, first of all, let's just see if this builds. So we're gonna do that. Let's see. Mac platform. Okay. Build it. What do we got? Okay. Cannot initialize, okay. Parameter of NS error. Auto releasing. Okay, so yeah, it's just I forget how we're supposed to how I usually end up doing NS errors. I think it's something like NS error. We're not going to be too worried about that right now. We'll do the error handling in a little bit more detail. So maybe I'll just put it to do here. That's like, look at error handling more closely, right? just to kind of clean up, right? So I just want to make sure that we're not having any issues there. Oh, what's going on? Cannot initialize a value of type NSError star. Oh, NSError nullable. Okay. So I guess, interesting. Is it really that we have to do NSError star underscore nullable star with an L value of type? Okay. So I guess with NSError nullable, that's nullable just means that it can be set to nil, or it can be a pointer that doesn't point anywhere. So interesting. Passing argument to parameter error here, right? Okay. Parameter type NSError nullable. Yeah, so we have a non-nullable NSError, I guess. Oh, what do I end up doing? I just want to look up really quickly. I forget what I ended up doing there. It's probably some dumb thing. I know I keep doing this. Okay. So oftentimes, oh, okay, because it wants a pointer to an, okay. So we can just do this. Okay. And then we just, yeah. Okay, so it just wants a pointer to that. I'll explain in a little bit. All right, and so that builds. Excellent. So we can just do alloc init on MTL render pipeline descriptor. So it's as I thought. And then we're just going to set the different properties of it. Error, right? So we're gonna dereference this error. It wants a pointer to a pointer of errors, which I'm not entirely sure why. We'll kind of get into handling NS errors. I generally don't love this particular style of programming, and the only reason that we're doing it is because we're kind of forced to through Apple's API. But this is basically like an exception handling kind of a style of programming things. And generally, I don't use exceptions. Like something either needs to succeed, like hard succeed or hard fail. And I don't love things that, we get an error back and then we can maybe what we do is we, pass it on to the next process. I just think that's bad programming. And there's actually some evidence that suggests that a lot of, from a fairly comprehensive study, that suggests that exceptions are just generally a bad idea. So we're actually gathering some scientific evidence that we really shouldn't be using exceptions in programming. But that said, we have to do it here. So we create an error object, then we pass a pointer to the error object into this error field. If it comes back with an error, we're going to hard crash the app later on. So I think we would just do like a global NS exception to hard crash the app. But we're not, we're gonna deal with that later because I don't want to get to that quite yet. Handle any errors, hard crash the app. Actually, you know what? Let's just do that if there is an error. So I think if error not equal to null, you can do something like NS exception, and then you can raise, and then so what I want to look at is the code for NSException. Again, these I don't love exceptions. I think they're terrible, but we're using it in order to if you raise an exception at the highest level, then it will just crash the app, and that's like one way to completely just cause the app to crash, and then we can tell it what to do. So the name of the exception, and then human readable string. So we're going to use raise format for this. So let's do that. So format string. We're going to call it can't set up metal exception. Format string unable to set up rendering pipeline state. So basically, if we don't have those in there, like, we're screwed. Okay. This will just hard crash the app, which is what we want. Will this give us problems? Format okay. Do we have to? I mean, I probably got the argument name wrong. Something like that. Let's take a look. No, name, format. Name. Oh, maybe they're not supposed to have a. No commas. Okay, yeah, so we can do that. Basically what this is going to do is, if there is ever, yeah, this is what I like to do. I'm okay with exceptions at the global application level. So this is at the level of just the main setup code that starts the application. If we have an exception there, that's fine because it will hard crash the app. Where evidence has shown that exceptions are really, really bad is when you have exceptions kind of like bubbling up from the lower, like from, say, some class that's a subclass of some other thing. What researchers have found is that oftentimes people won't actually handle the exceptions that come in from the different subclasses. So if you have this like really complicated system where exceptions like bubble all the way up, quite a large body of research has shown that that what ends up happening is these programmers tend not to even like handle the exceptions, and so the app is just in this like kind of crappy buggy state, and it probably should hard crash or it should hard do something, but it doesn't do that. This is okay though, because at the top level, as soon as there is an exception, the app is just going to crash, and that's exactly the behavior that we want here. So we need to be able to set up this render pipeline state. If we can't, we hard crash. That's the idea. Now this isn't going to really do much for us if we don't have a vertex function and a fragment function. You may have heard of these being called something else in other contexts. You may have heard of them called, well, yeah, actually the vertex function is probably the same, but the fragment function is also known as the pixel shader. So vertex function, vertex shader, pixel shader, fragment shader, same thing. So basically the same thing. We need a vertex shader and a fragment shader, or a vertex shader and a pixel shader. And those are the different functions that we're going to set up. We're going to create those in the metal shading language, and then we're going to tie them to this thing. So let's look at what we can do with that. So vertex function, right? So this is a type MTL function, vertex function. So we're going to look at what we need to do is something like set vertex function, right? And then we're not varx, set vertex function, and then set fragment function, right? And there's, some stuff there, right? So we're going to be doing those two things. Now, where do we get these functions? I have no idea, but let's look in the documentation. Well, I have some idea because I've done it before, but I'm pretending that I don't. and I'm just going to read the documentation by clicking through. So where do we get one of these functions? MTL function auto specifies which shader metal pipeline calls when the GPU executes commands to specify that pipeline. Okay. Okay. MTL. Don't use standard allocation initialization techniques to create MTL function object. Instead, use the function creation methods provided by MTL library protocol. So where do we get MTL library? Well, let's take a quick look at that. To create a specialized function, call one of these MTL library methods. So let's look at this thing here. Okay, MTL. So MTL library. Okay, new function with name, constant values. Set of constant values with constants. Provided. Okay. I'm looking for. I'm more interested in this MTL library thing. Okay, so what can we gather from this documentation? So it's a protocol. MTL library object contains metal shading language source code that is compiled during the app build process. Don't implement this protocol yourself. Instead, use the library creation methods provided by the MTL device protocol. To create an MT library from a precompiled metal library, that's what we want. Call one of these MTL device methods. So new default library or new library with file. So remember, this is on MTL device. We already have MTL device. That's like a thing that we've got set up, and we're going to be creating one from a file. So so new library with file and then error, right? So again, what we're going to end up doing is we're just going to end up like percolating this error back up. And if any of these things in the chain of succession of starting up the application, if any of them gives us an error, we flat out crash. So that's called actually caring and being a good programmer. So we're going to copy this, and that's going to be on MTL device. So this is before, I would say it's, maybe roughly before So we'll just say this is set up the metal library with Vertex shader and fragment shaders. Okay. So we need one of these things, right? So we're gonna say, hey, we'll just call this the shader library, right? Because that's what it is. That's where we're getting it from. MTL device or metal device, and then we can just call new library with file, ns error, right? Okay. So let's just percolate this error back up. We're just going to move it up, and now we've just got this error. And now we don't know where this file path is yet. We're actually going to talk about what that is. That is a thing that we're going to. I believe we're actually going to just put that inside of the app bundle itself. So I'll show you kind of one example of an application that I use, and what I do is I just precompile these things and I stick them inside the app bundle itself. So if I look at, I don't know, like how about my game Cove Kid? If I show the package contents, then inside of contents, inside of resources, that's this color shaders.metallib. That's a metal library. That's one of the things that we're going to load. And then we've also got texture shader.metallib. So that's another thing that we would load. And that's just got, compiled shader code in it. So this ends up going inside of the application bundle, which means that we need to get a file path into the app bundle. I forget exactly how I do that in my games. So well, first thing first, we'll stick the pointer to this error in here because we know we need that. And then we're also going to do something like this here again. Right? And then can't set up metal, unable to load shader libraries. Call it that. So we've got the error set up. The thing I'm less clear about is how I ended up getting that file path. I think what I ended up doing was, I think I had to end up creating. It might actually be simpler because sometimes you can use like bundle file paths. Basically what that is that's just your app bundle. Okay. Yeah, and that's what I did. I used a bundle file paths here. So we'll look at that. Okay. I just want to. Okay. So for different file paths, you can actually use this NS bundle main bundle. I should probably, come to think of it, I should probably I should probably use that a little bit more often. It's actually rather convenient. It's funny because like some of my other code, I don't really use that too often, but yeah, it's actually great if you're just looking for stuff that's inside of your bundle, which is basically your application directory or whatever. You can just tell it like, hey, you know, I'm looking for something with this name and this type, and then it can just like search through the whole thing and it can find it. That is usually pretty simple, and you don't really have to specify much in the way of like, hey, where is this located, or you know, having to come up with like fancy fancy file names and file paths and all that stuff. So you don't have to really do that, and that's nice. So we're just gonna call this. We're gonna say this is NS string star. Okay, so shader library file path, right? NS bundle, main bundle, path or resource. We're just going to call this, we'll just call this shader library. We'll just call it shaders. Shaders.metallib, and we'll just pass that into this new library file. All right, so at this point, I'm just going to make sure that this actually compiles. We're not running into errors and stuff. Do we compile? Okay, yeah. So obviously, that doesn't compile because we don't want it to compile because we need to get those. Okay, and I'm just going to get rid of my other thing here from the solutions. So we've got the shader library file path, and we're passing that in, and that's just fine. Once we've actually loaded metal lib, so shader library, at that point, then we can start to actually we can start finding the location of the vertex function and the fragment function. So these guys, and that's just from the documentation here. So if we go back to, let's see, new library. So we've done that. We've done new metal lib. This is a function. So new function with name. I don't think that we want. Maybe we do. Creates an object that represents a shader function in the library. The name of the specialized function. Constant. Okay, we actually don't do that. Pointer to an error object that describes compilation problems. If any, this object contains compiler. Okay. So I think it's new function with name. And that is, because what are the other ones? Actually, this is probably, yeah, we're not going to pass any constant. I think this is the one that we want. Yeah, because this is the simplest way for us to just get looking into a metal function. So I think we're just going to do this new function with name thing here. We're just going to copy that, and I'll kind of show you some of what that means. So, so again, just copying this thing, id mtl function, right? That is going to be our, we'll call it Vertex Function. Vertex shader equals shader library, right? And it's going to be a new function with name. And this name that we pick actually corresponds to that actually corresponds with the name of the function inside of the metal library. So in this case, I think we'll just call it Vertex Function, because that's typically what they're called by default when you just create a new metal file. And then we'll just do a similar thing here. We'll call it fragment shader. Fragment shader, shader library, new function with name, fragment shader. I think you just call it fragment function. What I want to show you is some of the some of my shaders that I've used before. So metal, texture shader.metal. Okay, so this is usually kind of what a shader ends up looking like, and you end up kind of, this is a more, we'll go through each of these and we'll kind of like walk through it. But in other, basically you have a function that's called Vertex shader. So that what I'm just trying to say is that the name that you pick here inside of this file, it needs to correspond with the actual name in the metal library. And if it doesn't, then it's just you're just never going to actually have your function. And so it's, you should hard crash if you can't actually like load the shader functions, right? That's what we're going to do. But if the name doesn't correspond to this function name, then it's not going to work. So in this one, I called it texture atlas fragment shader. That's probably way more than what you would need. I think if you just call it fragment shader, that's fine. So just make sure that the names match. The name of the fragment function and the name of the vertex function should match. That's all. So, and that's what we have here. And presumably, at this point, we can just copy this into the set vertex function and set fragment function, right? So now let's just take a look and see if that will compile for us. And unfortunately, this the tutorial today is just going to be kind of a lot of boilerplate setting things up. It's not going to be. I don't think we're actually going to get to a point where we can see the drawing of the triangles or anything like that. But I think we'll get pretty close next time. So right now I'm just showing you how to get the basics set up, at least from the code side, and kind of how to work backwards. So let's build it now. Okay, it builds. Very good. This is probably going to crash when it starts up. We can find out. It should crash, actually. That would be expected behavior. Just given that we don't actually have any serious stuff here. we don't have a, okay, and that did crash, hard crashed. And let's see, new library with file path must not be nil. Interesting. Okay, so that kind of tells us what's up with this, with this exception, right? So an exception got thrown when we tried to create the new library, and that's actually very valuable. Very valuable to know. Basically what it means is there was not a metal library inside of the bundle, the application bundle, that that's named whatever we named it. So that's good, and that's what we expected because we haven't actually created the vertex shaders or the fragment shaders. So that would be totally in line with our expectations here. So now, now that we kind of have this thing set up to actually load the stuff, we can start thinking about, let's see, what are we doing on time here? We're 45 minutes. I'm kind of wondering, okay, what should we spend a little bit more time on? We can start to get into actually, yeah, let's definitely spend some time on, like setting up a basic vertex shader and a basic fragment shader, and then compiling that into a metal library, and then copying that metal library into the application bundle. I think that's like a pretty good use of time. So, well, let's talk about that. So, if I go back to this game, video tutorials, and we're here. And now this is where I would start to make the metal file. So I would hit percentage if I'm in this thing, if I'm in this NeoVim netrw thing. And I would just call it shaders.metal. And so now, we're going to actually be inside of a metal document that we can then compile as part of the it. So I'm actually gonna sort of cheat a little bit and just get like a very basic shader in place, and then kind of move backwards from that. A lot of that just comes down to I don't really create the shaders from scratch that often, so I usually just start with like a template. I actually ended up taking this from a template that Apple has, and so I ended up like just copying a bunch of stuff. And really, the boilerplate stuff is not the important part here. What's important is understanding what's going on. That for some reason, actually, yeah. I don't actually know how to get it to have that coloring, so. So this is just a basic, what I'm doing is I'm just creating a basic shader for basic shader that would just give us the ability to draw some colors in a coordinate space. So I'm actually going to walk through a lot of this stuff. I like that this is just called Vertex. This is called Vertex, and this one's called Fragment. All right, so we'll just kind of walk through this a little bit. Sorry that the coloring's not so great. Here's kind of what we're talking about. So obviously you need to include metal. So I think it's this metal stdlib thingamajigger here. And then much of this requires the SIMD libraries on Apple. SIMD is basically what it means is single instruction, multiple data. And if you think about it, basically what a GPU specializes in is running a lot of single instructions on multiple data. So you could run the same instruction on a very, very wide buffer of data that represents the pixels that are to be drawn, right? And so you can have single instruction, multiple data instructions on a CPU, and we do have those. But we also have, of course, the device that is specialized for that particular kind of computation, which is the graphics processing unit, or the GPU. So it is focused on single instruction, multiple data, with very, very, very wide bits of data, which would represent the actual pixels that we're drawing on the screen. So these are, what's called SIMD operations, and Apple uses a SIMD library to do that. And it has a number of these different types in there, things like float4. So float4, what that is it's a four-dimensional vector that represents the position of something in space. And well, it really could be anything. So four floating point things. You can represent a color as a float four, as a four-dimensional vector. So you could think of it as having red, green, blue alpha values, just in as a single vector there. So that's kind of a wide piece of data, you could say. And we're just defining this structure. This is basically like, if you've ever done a vertex shader or a fragment shader in other shading languages, this is like our input data. This is our input data into the vertex function. And, well, actually, wait a second. And it's also the input data into the fragment function. Now, you don't necessarily have to organize it this way. I think you could choose to organize it a number of other ways if you wanted to, but it's kind of it's one of those things where oftentimes in other shading languages it is organized differently. So I'm just using Apple's example here. I'm just kind of like walking you through it, but you could do it some other way. And what we're going to do with this one, so actually this is kind of interesting. The default one that I used here, so a vertex function, what the vertex function does is it's meant to translate a vertex buffer that you define or that you allocate, or an individual position, a vertex, and it's meant to transform that into something in a different coordinate system that represents a specific view into your three-dimensional world. This is oftentimes called a projection. So in our case, what we actually want is a two-dimensional representation. What we want to do is we want to take kind of this three-dimensional vertex idea, and then we want to, it's called an orthographic projection. What we're going to do is we're going to project it onto like a two-dimensional space right in front of the camera. And what we want then is for the coordinates of that space to actually match the coordinates of our game world, so that if I say, you can imagine that, like, let's say that our screen, let's say that our screen is like 1400 by 600 by, I don't know, by 1024, or 1024 across, or maybe 1400 across, 1024 up. If I say that something is in the bottom corner, like 0, 0, and then the other edge of the rectangle is at like 200, 200, I want that to match what the GPU understands and what eventually gets drawn. And the problem is that vertex shaders typically, or rather the default device, the default coordinates in shading languages go from -1 to 0 to 1. So we can actually look that up. It's called normalized device coordinates. And I'll show you kind of what this means. We'll sort of like look at it through examples. Actually, is this there might be some better visuals here. Okay. 2D positions. Right. Okay, yeah, so here's a good example of normalized device coordinates. So this cube is actually an illustration of normalized device coordinates. And what it means is that in terms of the way that the GPU frames things, or in terms of the way that Metal frames things, everything is drawn on normalized. First of all, just generally means we're going to take a value that ordinarily encompasses a very large range. So if in your game world the actual screen is represented as even just on your screen, let's say that I have like a TV screen or a computer monitor, and it's like 240 by, or no, 200 or something wide by 2400 tall, just as an example. Okay, that's like a much larger range, right? So that's like you can go from 0 to 3800 on the x-axis, or on the y-axis you can go from 0 to 2600, something like that. To normalize those coordinates then would be to take that much larger range and shrink it down so that it fits between 0 and 1 or some smaller range. And that's basically what's going on here. So we could normalize that range in a lot of different ways. You could have it go from 0 to 1. For example, that's one way of normalizing that larger range. And then everything in between is actually just like a fraction of that larger coordinate. So you could represent 0 to 3800 as some fractional values between 0 and 1. In this case, in Apple's normalized device coordinate space, the way they've done it is they've set it up so that -1 is like the farthest to the left that you can be, and +1 is the farthest to the right that you can be, and then -1 is the farthest down you can be, +1 is the farthest up you can be. And then there's also the z-axis, right? So there's this, -1 is the closest to the foreground that you can be, and then the closest to the background that you can be is 1, or the furthest away that you can be is 1. And so that's actually really important to understand. Ultimately, you have two coordinate systems that you're translating from, that you're working with. You've got the coordinate system of your game, which is going to be much easier for you, the programmer, to reason about. It's much easier for me to talk about something being at pixel position 2800 than I can understand that a lot more easily than I can understand something being at pixel position 0.75576 whatever. So what you end up having to do in a lot of these games, or in a lot of these game engines, you have to translate from your they even have a thing here saying this more or less. You have to translate from your application coordinates, which are your coordinates. It's your easy to reason about human version of coordinates that you can talk about. You can talk about something being at a certain space on the screen, right? That's pretty easy to talk about. You have to take that number, and then you have to provide a mathematical transformation on it so that it fits between -1 and 1, right? In all three axes. So there is a mathematical transformation that you have to do. And basically the purpose of the Vertex shader is to do that transformation of coordinate space. It's to do the transformation from your application coordinates to normalized device coordinates. And this isn't necessarily the same on every shading language, which is kind of a pain in the butt. I think I could be wrong about this actually. But I do think some of them, they go from 0 to 1, or some of them go from -1 to 1. So you have to take the coordinates from your game world space, and you got to move them over to this normalized device coordinate space. Anyway, what I kind of want to go over is just some of what that actually amounts to. And right now I want to say we're actually going to simplify this thing. Here we're going to exclude this viewport size parameter, and we're gonna take that out. And I just want to simplify. I want to simplify this so that you'll see. So we're not. I want to show you what this looks like without doing any of this kind of without doing any of this fancy stuff. I just want to show you what it's like without doing any modifications to it. And the reason I think that's important is because once you can see what it's like to actually like draw the triangles in normalized device coordinates, if I can show you that, then I think it'll be a lot easier for you to understand how this transformation happens and the kind of math that we're going to apply to it, so that we can get it just drawing a 2D game in the coordinate space that we think is important. So I think that's going to be a really good idea. And then so in this case, I think we want our out position to just be pixel space position dot x, and then pixel space position dot y. Okay. And then let's see. So this will actually have the position. So we're basically not going to do anything to. We're not going to touch any of the actual coordinates that come from this thing, and then we're going to just talk about it in normalized device coordinates first, and then we'll kind of move that into mapping it to the actual viewport. So I think that'll help us out quite a bit. So what we're going to do now is we're actually going to try and this is probably I forget exactly what. Yeah, so we need to this does take in a vertex array, an array of vertices. So we need to actually we need to come up with like this struct of vertex arrays. So we need to make something like that, something that is our vertex array. And actually this can just be buffer 0. You can give it a name if you want to, but it's actually not important. So let's see. We'll just call this game vertex. And it's just got float for position, right? That's all it has. Yeah. So let's do that. Let's see if we can get this to compile. Okay. Vertex array. This always takes in, basically when you bind, you're going to create a vertex buffer. I'll show you this a little bit more closely later. And then you're going to bind it to this vertex shader, and then it's going to do some math to transform the points from your application space to normalized device coordinates. So that's what that's going to do. I'm going to we're going to try and compile this. So generally speaking, what I do is I compile the shaders before compiling any of the other stuff. So what that means is once we're inside of our build directory, I don't actually remember what the command is to draw or to compile these shaders. So let's look at that. I think I had this in a common build steps. Oh. Yeah, okay. There's a lot to get into here. So it would seem very, yeah, let's just kind of, okay. So XE run, what that comes down to is that is one of Xcode can actually run its various functions inside of the command line. So if you use this XE run-SDK Mac OS X Metal, you can also tell it what version of Mac OS you want it to support. This is probably not important. We can just take this out for now. I forget what line tables only is for. I think -G is also says, hey, like we want some actual debug information here. So we're going to call this shaders.metal because that's what we named it. And this is in the Mac platform layer path. And then you end up taking it, you make an air library. So shaders.air. And then you convert it into a metal lib. It's like the second step that Apple makes you do. Shaders.air to shaders.metallib. Okay. Now, if there are problems, we're gonna find them out pretty soon. It takes a little bit longer. Okay. Oh, interesting. Okay. So, yeah. We got a few problems. We are building this thing. Color, vertex array. Okay. So actually, this is, interestingly enough, no different. This game vertex structure is no different from the rasterizer data. You'll see that, hang on just a second. So we're gonna move this to the cross-platform game library. So the idea here is we actually take this. We're gonna have some kind of a cross-platform concept. It's called a game vertex, whatever you want to call it. And we're gonna have an array of these. They're gonna be somewhere in memory, and that is going to be an input into this vertex shader function, and it's going to do some math on it. It's going to convert that into some output that is in this rasterizer data structure. Now this rasterizer data structure is going to start having a few more other things in it later on. Kind of gets a little more complicated than it is now. But once we have that, we're then going to that will then output. You say we have return out. So this thing returns rasterizer data, it returns this output, and then it feeds it straight into this. It feeds it straight into the pixel shader. So it is like a pipeline. So rasterizer data in. So basically what's going on is it's taking the out parameter from here and it's using it inside of this fragment function, and then we're going to do some sampling on it. We're going to maybe get a color out of it or do something with it, and then we're going to eventually the GPU is going to draw it. So I just want to give you a sense of like what the actual pipeline looks like here. We take vertices that we're going to tell the system how to fill in the colors, and we're going to take that from a cross-platform game library. This same concept is probably going to exist, is probably going to be used or cross-compiled on other platforms that this game eventually supports. So it will be compiled on Windows. It'll be compiled on WebAssembly. Even if this becomes like a real hit of a game, then like we're talking about putting this on Nintendo Switch. So there's going to be this idea of eventually, you know, cross-platform structures or cross-platform stuff. And so this is actually the start of that. So we take a cross-platform thing and we put it through our graphics pipeline into a Vertex function on the Mac platform that transforms it from our own special application coordinates to normalized device coordinates on metal. And then once it's done that, it then gets passed into the fragment shader that then samples the individual pixels as it's drawing these triangles to decide what color to fill it in with. That's kind of the high level view of what's going on here. So that was one of our errors that we just, oh yeah, and then we also need to have a semicolon. No, that's not what I want. Okay, thank you, Vim. I love Vim because you can just like screw up in a lot of funny ways, and thankfully it's easy to recover. Okay, so it built that with no issues. And all I want to show you is that, because we are kind of getting to a point where we're sort of near the end here, and on the next one we'll get into more of actually, hopefully actually drawing stuff. What I wanted to show you is now in our build folder, you see that we have this shaders.air and this shaders.metal.lib. So we actually did just build a metal library with a vertex function and a shader function that we can use in our game. There are a few other steps that we need to do. We need to copy this metal lib into the actual game library. How are we doing on time? Yeah, okay, we're doing pretty well on time. Let's, I mean, that's not a hard thing to do. So let's just copy that. So what I want to show you is, hopefully what we can do is, well, I know we can do it. We're just going to copy it. We're going to copy this thing from, we're going to copy this into the app bundle. So we're going to say cp Mac platform layer path / shaders dot metal lib to the app bundle name / shaders.metal.lib. Right. Actually, maybe we put it in the contents directory. It kind of doesn't matter where it is. So we're going to run that now. All right. And now what we should see, if we can, now inside of the bundle, you should see that we have, oh, we don't have that. Dang, why don't we have that? Oh, right. We don't have that because I'm a fool. And I was trying to copy it from the platform layer path, but that's actually not where we're copying it from. We're copying it from like right here, right? So we're actually just copying it straight from the build path. Yeah, no such file directory. Okay. I should have actually just paid attention to my output messages. Okay, this I think will have worked. And if we look at this, show package contents, shaders.metal.lib. So now all we did was we just copied from the build directory into the actual application bundle. So that's all we did. Now if we run this, it shouldn't crash, I think. Oh, it crashed. Okay, but maybe it crashed somewhere else. File path must not be nil. MTL library, new library with file. What did we call it? Maybe I just didn't call it the right thing. Let's take a look. Okay. Shaders of type metal lib. Well, dang. That, oh, path, maybe it needs to be under like some other thing called resources. Okay, if I look at my other one, yeah, there might just be like some specific, I'm gonna see, I'm just gonna make sure that I put it in the right path. So this is, you know, more the full game here. Contents / resources. Okay. And I ended up putting all of my metal libs in there. So that's probably what we need to do instead. So content / resources. So we're going to make this content / resources, make that directory. I know I probably did that really quickly, so I'll just show you what. When we make the bundle directory and stuff, you got to make all of the other directories like a few levels deep here. So we created the contents directory, and inside of that we created the resources directory. So that's just going to set us up so we actually have all of those directories first. You need to create the directories before you start filling them with stuff. That's what that was. And then I just change it so that it goes into this resources folder. So these are just kind of like funny, you know, I think this bundle for resource thing is like actually pretty specific in terms of what it wants out of you. So I don't know what to say other than that. It's just kind of a thing. So now we go back to here and we go to, what I'm looking for is like a certain structure, contents, resources, shaders, okay. And now what I'm hoping is that, okay. Well, it's a different crash. Failed assertion, render pipeline descriptor validation. Vertex function must not be no. Okay, so there's probably something that we got wrong here. So I'm guessing that it's probably the name of the vertex function. So if we look at that, we hit some kind of thing. So we call this vertex function, fragment function. And this is actually just called vertex. I know it's called vertex shader. Okay. Is that the case? That's called vertex, and that's called fragment shader. Okay, so if we just name these differently, then they should load up. Take a look. Okay. Okay, well now we're back to the green. So that's actually great. The fact that this didn't crash, just hard crash on startup, means that we've done a few things here. We've compiled the metal library. We've compiled our vertex shader and our fragment shader into a metal library, and then we've copied that metal library into the application bundle. And then on startup, we had metal like load those functions, so load the vertex function and the fragment function, and then set that up in a pipeline state descriptor and a render pipeline state that we can then use on a render encoder to tell it how to draw some geometry. So we actually successfully did all the boilerplate code for setting up just metal with one vertex function, one fragment function, to get us into like prototyping some two-dimensional games. So that's awesome. Good. I think that's a good place to stop. So if you like this, if you found it useful, by all means, subscribe, Patreon, send the link to your friends, let them know you're making a game from scratch on your Mac. You're not using any engines. You're using some libraries, and you're learning a lot about programming. So this has been fun, and I will see you next time.